Hi, and welcome again to my Physics Online video lecture series. Today's video is about the Biot-Savart Law. So in this video, we're basically discussing the sources of magnetic fields, and we are looking at a law that allows us to calculate magnetic field strength at a given point in space. In some sense, you could think of this law as being the equivalent of Coulomb's law for figuring out electric fields, bearing in mind, of course, that with electric fields, and the same is going to be true for magnetic fields, bearing in mind that you use these laws largely to figure out what is the field going to be at this one location in space, and then from there you might have to go to another location in space and reapply the law. So this law actually pertains to a particular location in space. It calculates using actually differential currents in order to figure out what that field is. So in some sense, what we're starting off by saying is that current is the source of magnetic field. So current, of course, is moving charges. So moving charges create magnetic fields or cause magnetic fields. And just in the same way, we might recall that charges in general, whether they're moving or not, are the source of electric fields. And this whether they're moving or not clause may be of some interest to us in a future set of lectures, but for now, we'll kind of set it aside. So charges produce electric fields. Current, moving charges, produce magnetic fields. And with the electric fields, we used Coulomb's law. With magnetic fields, we use the Biot-Savart law. And this Biot-Savart law, I can basically state it. So let's actually begin by stating it, and then we'll break down what it is that the Biot-Savart law components are doing for us, and then maybe have a quick example. So Biot-Savart law basically allows you to calculate some differential magnetic field, dB, by using current. So let's say we have mu naught times I divided by 4 pi. And then the differential portion of it is this little cross product, dl cross r hat, divided by r squared. So in some sense, this right here is your Biot-Savart law. We now need to kind of define some of the terms within it. Before I do that, though, I'd like to note that the magnitude of the magnetic field, that is just dB, or if you prefer, modulo of d vector b, would just become mu naught times I times the sine of some angle theta times dl divided by 4 pi r squared. So what is this angle theta and so on? Basically what we have to do is sort of draw out for ourselves an imaginary scenario. Let's say that I'm wanting to calculate dB at this location right here. So this is, we'll say this is dB at point P. All right, now let's say that we have down here some current, and the current could be a straight line current, it could be kind of wiggling around. So we have current running through this wire. Now let's say that within this wire we want to figure out current, we want to figure out the field due to current in this location right here. So we know from our basic circuits stuff, DC circuits for example, the discussion about Kirchhoff's rules, that the current, it should be the same everywhere within this strand. Let's say that this is a wire, for example, that's just kind of windy. we know that the current here and the current here are the same, so I don't need to have a differential current dI to do this. However, I do need to note that this has differential length dl. And how do I figure out differential length dl? Well, I draw this tangent line at this point, and dl would just be like this differential right here. Okay, so again, this is from this point. And now, what about the r portion? Well, if I draw a line running from here to my point P, pointing from this location at which I'm looking at this particular differential contributor, this little this current in this little length of wire, then this would represent vector r. And if I put in an angle running from dl to r, remember how cross products work, if I put in this angle theta, that would be the theta in this equation down here. Okay, so I've now defined for myself all these things, because I also, I suppose for completeness, could define an r hat. So r hat is the vector that points along r but has unit length. So this is a cross product with r hat, not with r. If you'd prefer, some people actually write this equivalently as dB is equal to mu naught times I over 4 pi times the cross product dl cross just simply r, and then that would be divided by r cubed. So in some sense, reminder that r divided by r is just defined as r hat. Okay, so we've now got for ourselves everything in this equation except for this term right here. So this term is what's called the permeability of free space. And we will have cause to talk about it again when discussing Ampere's law. In fact, I may even give you the definition again for it then. This is permeability of free space. It's a fundamental constant and of the universe, and it has a value mu naught of about 4 pi times 10 to the negative 7. And then units of magnetic field, you'll recall, are Teslas. So it's actually Tesla dot meter per amp. So in some sense, this is the other important boxable thing, because this doesn't change. Why do I say approximately equal to? It was originally kind of like defined to be this, but with our definition of what are the most fundamental base constants and what are fundamental constants that are derived from those other more fundamental base constants, the speed of light in vacuum is a fundamental, defines our entire metric system measurement kind of constant. Mu naught, it turns out, is related to the speed of light via the permittivity constant, which is something we'll talk about in a future lecture as well. So it turns out that if you have an exact defined value for the speed of light c, then either mu naught or epsilon naught has to have a measured value that is good only to the precision with which we can measure it. It turns out mu naught is the one that has such a value. Okay, so in some sense that is the Biot-Savart law. As we've said here, it's the equivalent to Coulomb's law for figuring out what is the magnetic field. Putting it all together, you have that the magnetic field strength at location P should be the integral along essentially the entire path of dl. So you could say from one end of the path to the other end of the path of dB. And so I kind of written this in a funny way. Maybe I should write it with those integral terms L naught and L final or L end or whatever. And then you'd use your Biot-Savart law. So you'd have your mu naught times I, which typically the mu naught, the I, the 4 pi, those are usually constants. So those usually actually get to come out of the integral. So we can say like mu naught I over 4 pi. And then essentially we end up with this dl cross r hat divided by r squared. So the differential that we're using is this dl differential. Here's maybe where we would put in our endpoints L1 and L2 or Li and Lf or whatever you want to call them. And so the tricky thing left is essentially this cross product dl cross r hat, and figuring out what r squared is doing is usually the difficult part of this integral. And to emphasize that, let's maybe do a simple example. So a relatively simple example is a very long, very straight wire. And in a future lecture, we'll actually talk about another way of calculating this for what it's worth. So we're looking some distance x away from the wire. We have some current I in the wire. And we might ask, all right, well, let's say that this right here represents my dl. And so r would be essentially this vector right here. So what's the trickiness of this problem? Well, essentially r is changing depending upon where you've chosen as your point on the wire. So, we could say we're integrating from minus infinity to infinity over this, but now we'd have to figure out a function of r that goes with the wire. Now, we might note, for example, that dl is dy, and so in some sense, our integral here has become b is equal to mu naught I over 4 pi integrated from infinity to minus infinity of dy cross r over r squared. All right, fair enough. Now, we may note that the r squared terms, the x term, and this cross product can be related so that instead of having multiple variables, we have a y here, we have an r that is somehow a function of y. Instead of having multiple variables, we'd like to reduce as best we can to one variable against which we integrate, and then a bunch of other integrals a bunch of other variables that we do not integrate against. One way we have of doing that is to go back and essentially recall that we really care more about the direction, the magnitude. The direction we can figure out using unit vectors or the right-hand rule. To find the magnitude, though, this becomes b is equal to mu naught I over 4 pi integral minus infinity to infinity of dy sine theta over r squared. And so in some sense, we have a y, we have a theta, and we have a little r that are all variables in this. To make that clear, I've drawn on here theta. And so if I were to pick a different dl, like right here, so this is just a different dy location, I would have a different r, which I'm going to mark as a prime, and I'd also have a different theta value, which I can mark as like theta prime here. So these are all kind of related to each other. I have one constant in here, which is my x. And so I look at this and I realize that in both cases I have for myself a right triangle, and that means I should be able to cast the location at which this is happening. Let's call this y, and maybe this one y prime. This y value and this r value can be related to theta and to x. right? So by doing this, what we have done, or what we would be doing, is reducing from three, let's say, interdependent variables down to one variable and one constant, and that makes the integration a little bit easier to handle. So how are these guys related via this right triangle? Well, I can see that for my r values, if I have y squared plus x squared, I get r squared. And if I look at x and y, I can see that in some sense, tangent of theta, so using, for example, this interior angle, tangent of theta, I have my opposite, that's x, divided by my adjacent, that's y. Now, let's make one kind of odd choice, because this right here kind of makes sense from looking in triangles and so on. I'm going to actually add a minus sign to these two, and what that is about is, instead of measuring down, let's measure as being upward, being sort of our positive theta, and so that involves putting a minus sign in here. Be that as it may, what does this actually do to our system? All right, so if we have r squared is equal to x squared plus y squared, and also y is negative of x divided by tangent theta, we can kind of come to this equation where we see an r squared and where we see a dy, and basically substitute. So, okay, this right here, we need to figure out what dy d theta is. So we are basically taking a derivative of this negative tangent theta. The x just kind of goes along for the ride because it's a constant in this case. And so essentially that means that our dy term can be substituted for x cosecant, so CSC squared theta d theta. By definition, cosecant squared is the same thing as 1 divided by sine squared, and so this right here by definition must be x divided by sine squared theta d theta. All right, so now what we do is we ask, what is the sine of theta equal to? So coming back over to this triangle, if I take the sine of theta, that should be opposite divided by hypotenuse. So sine of theta should look like x divided by r. So this term here should become dy is equal to x d theta divided by x over r quantity squared. And so if we kind of square it out and reduce, simplify, I end up with r squared x d theta over x squared, which is just r squared d theta over x. So now if I come back to my Biot-Savart law and plug everything in for this dy term, then I'm able to substitute in this r squared d theta over x. You may be tempted, by the way, at this point to notice that there's a sine theta is x over r and make a substitution here, but don't do that. Remember that what we're trying to do is get stuff in terms of thetas and x's, not in terms of r's. So this substitution is actually counterproductive because you already have a theta here. You don't want to introduce more r's if possible. So this term right here becomes mu naught I over 4 pi, and we're going to have to figure out our limits of integration because we're getting rid of the y's, so now we need to know what it is in terms of theta. We'll do that in a second, but some of you may be able to figure it out before I even tell you this. You have an r squared, you have a d theta, you have a sine theta, and then that's over r squared times x. And so the two r squared terms can cancel each other. That's why we didn't want to do anything with this sine theta term, because now I have an integral that's in terms of x, which is a constant, so x can actually be moved outside of the integral, and of theta, which is not constant. What are the limits of integration? Well, coming back over here, if we were to start infinitely far away down here, then our angle ends up being what? And if we start infinitely far away up here, what does our angle end up being? And that is going to determine our limits of integration. For my choice of how everything has been defined, it's actually kind of easier to go from this point, let's say, up to this point, and then, or from this point down to this point, and then double the value of the wire, knowing that the top half and the bottom half are going to give you same contributions. And so that would give you limits of integration from 0 to pi over 2, but you have to have also a factor of 2 out front. You could also choose your angle in such a way that the limits of integration are from 0 to pi, as it turns out. Either way, the key integral that we're doing here is sine of theta d theta, and that, you know, is going to be negative cosine of theta integrated from these two limits, so from 0 to pi over 2 with this factor of 2 out front, so 0 to pi over 2. You know that the cosine of 0 is 1, you know that the cosine of pi over 2 is 0, so what we have here is negative 2 times 0 minus 1, and so put all that in, you get 2. Then you got to multiply by all this other stuff, and so b ends up being 2 times mu naught I over 4 pi times x, and therefore our final answer is b is equal to mu naught times I divided by 2 pi x, where x is the distance from the wire to the point where we're trying to find the value of the magnetic field. Now, you may be also asking, what is the direction? So what about the direction? Well, again, your dB, and we can call this like a dB hat, so this is just strictly the direction, should look like dl hat cross r hat. Put differently, we can look at the direction that r is in, we can look at the direction dl is in, and we can take the cross product. So if we were using unit vectors, then that means you're going to want to take like an ijk matrix, and you can go review how to do that. This video is a little overlong, so I'm not going to do all that in here. Your other option is to use what's called the right-hand rule. To use the right-hand rule, I've drawn on here two sets of green vectors, and I'm going to label that RHR for right-hand rule. You take your right hand, this is my right hand, you take your right hand, you point your index finger until it points in the same direction as the vector that represents your DL. So DL gives you the index finger. Your middle finger, you have to rotate your right hand until your index finger is still pointing along the DL, but you want your middle finger to be pointing along the value of the R. And so basically you rotate them around until you have that condition met, and you want them like more or less like closed, like no contorting the middle finger out. It being pretty hard for me to show on the camera because the camera does a bunch of mirroring stuff, but this right here is my index finger, and it's pointing in the same direction as the green arrow marked index finger. This is my middle finger. It's more or less pointing in the same direction as the arrow for middle finger. My thumb is pointing out of the screen at you. And so this suggests that the B field direction at this location is actually out of the screen. Better than that, I'm not going to be able to show with the setup that I have, just because there's a lot of weird mirroring with the camera. And so it takes some weird contortions to show on the video screen what actually matches on the drawing. It's like I can very easily do it for myself and get it to point out of the screen, which actually would be this way for me. But for you watching this at home, you know, this is the direction that's out of the screen. This looks like it's into the screen. So there you have it for mirroring. That's all for today's video. Hopefully you find this helpful. Hopefully you've learned something from it. Thanks for watching.